Swayam Prabha. Digital India. Educated India.
As I told you, this strength property is very, very important as far as the design of real structure in rock is concerned. So that's why based on the different types of test methods we can have we are testing for deformability test, shear test, strength test, and permeability test. Okay, and we have seen that more or less the 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 procedure of all these tests are remains same, but the difference is that we are trying to test a large volume of the rock mass rather than a small one. So we are testing a large volume of rock mass. So in last two classes, we had started with the basic introduction of this in situ strength, the requirement, and why it is what is the objective of these methods. Then we have seen the plate test, and in plate test we have seen the beautiful method. What is there are different procedures are there. We are trying to put some cyclic loads. We are trying to put some constant load also, and we have seen there is a purpose is related with that, and this constant load and cyclic load. If you are seeing at the constant load, we are keeping this constant load for about 3 days in a cycle. So if I'm following a 5 different cycles, so almost 15 days will be the duration of a test. Okay, so 15 days time we are applying the load, unload, load, unload for continuous 15 days. It can be more also, no? It will depends upon our requirements. So now you see, as far as the in situ strength test is concerned, 15 days is required for testing, and sometimes some days are required for your site preparation itself, no? Site preparation, drilling process, as well as arrangement of all these equipments and all that. So this test procedure is definitely taking a lot of time. Also it attracts a lot of money also, and it needs a lot of manpower also, right? So because of that, we are not going very frequently for this in situ strength test, but the need of this test will depends upon the type of structure we are creating. If the structure is of very important or very strategic in nature, then probably such type of test is must for on-site itself, right? So today I will just tell you another method which everybody will appreciate. That is called, which we have. I had given you some glimpse of that method in last class itself. That is called radial deformation test. So I was just preparing a photograph so that you will be very easy to understand this method, and I personally like this method a lot, and a lot of concepts will come into I will discuss a few concepts also apart from what we have already discussed, that will always come into picture. Now you see, in case of this method, this is one type of method where we are trying to test a large volume of the rock mass. Again, we are trying to test a large volume of the rock mass, and this is being carried out in a tunnel type of openings, right? Tunnel type of underground opening. Now you can see in this figure, I have tried to draw a earth surface, and there is some section of a part of a tunnel is shown, which is in horizontal. No? We can have a different orientation also, maybe some inclined tunnels also we can do this test. But for this one, we are trying to show a horizontal tunnel, and which is lying at a depth of some few meters from the surface. So it can be anything. No? So based on the type of tunnel you have created, we can do this test. And what this test is, going to the figure which is there with our ISRM, which is provided by ISRM. I will try to explain this method with few photographs. Okay. So now I think there is no problem that this tunnel having a circular cross section, maybe diameter maybe for 2 meter to 4 meter, no, depends upon our requirement or the purpose for which these tunnels are being created. And now what we are doing in next stage, we are looking at a particular section, and what we are doing, we are just look at this figure, we are identifying two section of this tunnel, and across this section we are trying to do something called we are creating a what is called a, a closed cylinder inside this tunnel, closed cylindrical space inside the tunnel, and those closed in tunnel will be created by some sort of a concreting all around, and maybe it will be closed from all the sides, so it is like a cylindrical box will be created. And you can see in this figure, we have created a cylindrical box by concreting from all the sides. From all the sides, this section of this tunnel is being concrete lining is being taken place, and a particular diameter of the uh, a smaller tunnel with concreting is being prepared for this test. So what we are doing in this test, when once this is being created, we are just filling with some amount of liquid into it. We are filling this area with some amount of water, full of water, and then we are applying some pressure within the water itself. And once we are applying a pressure, that will be your hydraulic pressure within this water, and once this pressure will be applied, it will try to apply some amount of pressure all along the sides of the tunnel. All the sides of the tunnel will be applied with some amount of pressure. Okay, so this is the one way of doing this test. Else, if the water is not suitable for that particular location, we can go for a flat jack. Again, flat jack systems can be installed over here to apply the load at the inner wall of the tunnel. Okay, so what is our doing here? We are applying the pressure from inside the tunnel, so that all the rock mass which is in and around this tunnel are getting deformed. And in this process, when we are applying this load, in this process we are trying to measure the deformation also. And for the measurement, and if I can draw a section of this tunnel, how it will look like. This section is being demarcated by A, B, C, D, and in this section you will find that this outer wall is showing you the finished diameter of the tunnel. Okay, and then we are applying some amount of concreting of particular thickness. Okay, we are putting some concreting along that, and then we have the another set of concreting. Once the installation is over, we have to close this tunnel also, and then on the inner wall of this tunnel, we are applying some amount, some sort of a MPBX. Now, MPBX we had discussed in the last class. Multi-point or the multi-position borehole extensometer is installed all along this tunnel. All along the tunnel, we are applying this MPBX, so that once we are applying some pressure, and so that we can measure the deformation at different locations. So we can have the 2-point or 3-point or 4-point based on the type of the tunnel and the type of load we are applying, we can use it. So once we are doing that, we can find out, the deformation, and we are applying the pressure. So you can find, so this is the principle behind the radial jacking test, where radially we are applying. Why the name is so? Because we are applying the load radially on the in this tunnel, and the because of this pressure jacking system, the hydraulic jacks, this test is being conducted. So we are calling it a radial jacking test. No? So this is one of the type of radial jacking test, when both the ends of the tunnel are what is called the blocked, and in this inner spaces we are applying the pressure either by hydraulically or maybe some other means, or mechanically also. When we are applying a hydraulic pressure, so sometimes what is happening if the rock is very fractured, or a term we are using that is called the permeable rock, or maybe you have learned about the pervious or impervious rock, means the rock which is allowing the water to pass through it, or the rock which is not allowing the water to pass through it. If such type of rock mass is there, based on that we will decide what type of radial jacking test, or the variation of this radial jacking test we are going to use it. So if the rock is very very strong, maybe some igneous rock and maybe of granite type of rock, where the pore spaces are less or very few, or pore spaces is almost zero, and it is impervious in nature, in that case there is no need to create this concrete wall also. We can directly close this tunnel from both the ends, inside and the outside. Both the ends it will be blocked, and in these two sides, from these two sides we are applying the hydraulic pressure. Okay, so if the rock is very very pervious in nature, impervious in nature, there is no need to apply the concrete wall, or that is a term we are using that is called shotcreting. Okay, shotcreting is a term which we are using in a rock mechanics or maybe geotechnical engineering to define a type of support we are applying to the rock wall, where it will this rock cement rock mixture or the concrete mixtures will be get or maybe we can use the iron bars also, so that it can have a thorough binding between the rock and the this type of material. So that is a term we are calling it as shotcreting. Okay, so shotcreting, rather than calling it a concreting, we can call it a shotcrete wall, is being created inside the finished diameter of the tunnel. Finished diameter of the tunnel means what? Finished diameter of the tunnel means the tunnel diameter which has been created by maybe the machine cutting or maybe by blasting. So that is called the actual diameter which has been created after the excavation. Then we are providing some support in terms of some concreting. So after the application of this concreting, whatever the diameter will be left, that is called the finished diameter of the tunnel. And after that we are going for this type of test by blocking from both the sides. Okay, now what is the problem when I am going to test radial jacking test with this finished diameter? Then two things happen. One thing happen, huh? What is going to happen? We are going to measure not only the deformation of the rock mass, but also the deformation of the thickness of this shotcrete. Hmm. So as the thickness of the shotcrete will be more, the deformation, whatever you are measuring with this instrument is going to give you the measurement, the deformation in the concrete as well as in the rock mass. So that is the one type of disadvantage which is associated with this method. So that's why we want this layer of thickness. Wherever we are not able to stop it, stop the application of the shotcreting, we want that this thickness should be more, or we can increase the strength of the shotcrete so that it can apply the required amount of support to the, and it can create an interface between the rock mass and the water whatever you are keeping over there. So as I told you, when I am using this water, it means that the rock is impervious, means it will not allow the water to pass through it. So then we can use the hydraulic water for this type of testing condition. Else, if it is not possible, then we can go for some hydraulic arrangement for apply the load. So why we are doing so? If I am going for this hydraulic arrangement and then we are going for the mechanical arrangement, the costing will be the factor. If I am going for the hydraulic systems, the cost will be less. When we are going for the mechanical, obviously the cost is going to be increased. So all the time we are very very cautious about the cost component of this type of test. So based on the requirement. Now one more thing, we are blocking from the two ends. We can block it from the one end itself. Other end we can look for the blind part of the tunnel. That means the end of the tunnel where we have not extended beyond that, and this end we can use it as a one end of the this enclosed area. Rather than
Okay.
using it for the
Like
two ends,
like
we can do it from the both ends, right? So
Lavender
that
your
thing
love.
can be done. That thing can be done, and we can see that we can we can decrease our effort of in or concreting on both the ends. So if we can use the one end of the tunnel as end of one of the enclosed area, and opposite end we can make a concreting. So this way also we can make a enclosed area of this test chamber, we can call the test chamber can be created by enclosing only at the one end rather than the two end. So we can do in both the ways. Now if the tunnel has been extended for long time, long length, and after that you feel that okay, I have to do this test at a particular interval, so then you cannot do that. So it is only possible once your tunnel is under progress and you have already identified that area. Okay, at this point of location, I want to have such type of test. Then only you can utilize the enclosed end of the tunnel, which is under progress, which is under excavation, and it may be excavated after few days or a few days time, or maybe it is excavated in future. In those cases we can use the one end of the tunnel for as a end of this enclosed chamber, test chamber. Okay, so this is about in nutshell about this method, and you can, if you look at this the figure which is available uh, in our standards, uh, and a very important thing here we have to have, if you look at this figure, it is given in a section. I don't think there is any problem. If any problems are there to understand this figure, let me know. And if you can see that we are applying the this is not a system where we are applying this hydraulic. Here we are applying the mechanical system of application of the load. Okay, and in this case we have a frame is there. You can see this frame, and that is called the reference frame. Now you can see we are calling it a reference frame. A reference frame is created along the axial direction of the tunnel, so that whatever the deformations are there, we can measure with that reference itself. No, that will be, and it is getting fixed far away from the load of application into the tunnel. So this beam is being fixed into this tunnel away from the point of application of or the point of where we are going for this type of test. So this reference frame is to be installed so that we can measure whatever the deformation is happening along this. Other important thing, as we have seen in our last class also, we can also measure here, because it is in three-dimensional body we are measuring the test. So definitely it is making a it will tell you about, this test will tell about whether the rock mass is isotropic or whether it is anisotropic. Okay, other advantage which is with the other methods is especially the flat jack method. This is going to give you the large volume, the volume of the material or the rock mass which is being tested in this test is more than what we are doing in the flat jack test, much more than. It will all depends upon the type of, as far as the concept wise is concerned, it all depends upon the type of the hydraulic jack you have, through which you can apply the pump pressure into this test chamber. No? It will all depends upon that. The capacity of your pump you can apply, as well as the type or the strength of the rock mass. It is not like that. If you have a pump pressure of high capacity is there, you can apply load much more and more load. No? Because what will happen if you are going to apply more load? What will happen? The rock in and around that area can get damaged. So we have to be careful while selecting this type of uh, instrument in a combinations. Okay. Now, if you look at the sectional view also, in a sectional view, and this is the system which is given for the mechanical way of applying the load. And in this case, you will find that this is your tunnel diameter, and then we have this concreting. No? We have this concreting, and then after that, we are applying the flat jack. Now, this seven, it is denoted by 7. This is 9. 9 is denoting what? The shotcrete, right? 9 is denoting the shotcrete is being applied all along the tunnel. The advantage of the shotcrete system is that it is going to give you a smooth surface of the concrete of your tunnel, no? And also it is applying a support. It is also applying the support to the system. Okay, so we are this 9 this in this figure, this 9 is showing you the shotcreting. Then we are placing the flat jack. Flat jack arrangements. We are putting flat these inflatable plates are being inserted into that, and after that we are putting some sort of a some sort of a that is called hardwood lagging, or maybe called the fixing, so that we can tight that area. And after that, it is better to see this number 20, that we are putting some steel rings are being placed all along. Maybe circular rings are being placed all along the tunnel, and after that we are fixing the space between this ring and this flat jack by some sort of a logging. Maybe this logging will be wood, no? Because the deformation of the we cannot use other types of material. The hardwood we are using, which we can bear a lot of stress when such type of loading will happen. And now we are this rings are being fixed into this wall, and after that we have another set of boreholes are being set over here, in through which your extensometers will be inserted into the wall of the rock mass. Okay, and this is going to give you this measurement. So all the numbers whatever is mentioned over here, 15, 16, all the captions are mentioned over here, so you can have you please go through that. And this is very obvious, and this is very simple method, and it is going to give you a large volume, the low deformation characteristic of the rock mass. Okay, so in short, we will see that what is the load we are applying. Again, we are applying for constant pressure for about for a 1 day, and we are applying a concrete lining all along. That is your shotcreting whenever is required. If it is not required, if the rock is very impervious in nature, no need to have a concrete lining. We can apply the load directly into the rock wall itself, and the rate of loading will be something like that, 0.05 megapascal per minute. We are applying the pump pressure at this rate. We are applying this load in a very slow way. No? That is called the static load. No? Slowly and slowly we are applying. The rate of loading is also affecting a lot as far as the failure is concerned. If the rate of loading is high, the failure load is something. If the rate of loading is less, your failure load will be something else. Okay, so this rate of loading is also deciding the strength of the material. No? So I will ask you, this will be possibly a very interesting problem, how the rate of loading is affecting the strength of the material. Whether it is an engineering material or the rock material, how the rate of loading is affecting. So that is going to be your assignment questions for the next week, so that you have to find it out and you have to answer in your assignment. Okay, so that's why I mentioned here rate of loading. So for a particular type of loading, I am trying to load the rock mass in a particular rate of loading, means that is called static loading. We are in the static loading, maybe some sort of a creep loading, or maybe the dynamic loading. There can be quasi-static loading. So different types of loading has been defined as far as the structure is concerned. So the failure load for will depends upon this one. whether it is a 1 megapascal, whether it is a 1 megapascal or 10 megapascal or zero point 0.0 megapascal. It all depends upon this, what will be the failure load. Okay, so the failure load is going to dependent on rate of loading. So whatever the test we are going to perform in the lab, this rate of loading should be defined. You have to be clearly defined for what rate of loading we are doing this test. Okay, so please find it out, and maybe after a few classes I will give you this answer also. Okay, so some test procedures are there which is almost same with what we did for the plate load test, and also here doing with the constant pressure and maybe the constant loading condition, and it can also go for a cyclic loading here again. Okay, so all similar type of test is being conducted for this radial jacking test also. Okay, so this is all about this test, and we can different types of cycle, and based on that we can find out, we can use the same relationships what was developed for the plate load test to find out the different modulus of deformability or for this test, for this condition also. Okay. Okay, so next test which I will try to discuss about, that is also a very important property, that is called the direct shear test. And before discussing this photograph, I can discuss this photograph first, in which we are trying to see that we are trying to find out, we are trying to shear away, or maybe like you can see here in this figure, I am trying to show you the two blocks are there, right? Two blocks are there, and which is connected at some location, some at along some plane, or this plane can be arbitrary also. It is not needs to be a very straight as it is here, but it will be a very uh, maybe very undulating or not plain at all. Okay, in reality this is happening now, it is not very plain. So we want to find out if a rock is jointed and there is no deformation has occurred along the joint. So what is the value, or what is the strength of that joint? So this, the strength of this joint will depends upon the type of rock material we have, or the type of roughness we have, roughness on the surfaces, or the type of interconnections, interconnection with the upper block and the lower block is happening, or the type of load which is being applied from the, like this can be a possible situations. Maybe if I can draw a simple photograph, like you have also solved it in your school, in your schools also, like say for example a slope. I can have a I can draw a slope very quickly, and if you can have a slope like this, and it's still not completed, so I can have a section of a slope. Some of you might have visited some of the highways in hilly terrains, and you'll find you can find in maybe you are traveling on this line. This is the roadway, and there is some inclined slopes are there. Okay, and if you can identify there is some sort of a discontinuity here, and it is passing through something like this. Okay, passing something like this, so we can find that on the surface of this discontinuity, so this discontinuity can be will be irregular in shape, right? It cannot be a very smooth as it is shown by a straight line. So it can be some smoothness, some what is called roughness will be there. So I can remove this one. For a model we are showing like a smooth line to fix our, to make it simple to find a mathematical relationships to be find. So based some undulations will be there on this, maybe this scale will be little higher as far as a comparison to the this is concerned, scale is concerned. So this looks to be very uh, rough, so it is not like that. If you can little mild also. So let us say this example. So what will happen is failure. So this slope can fail, either will fail definitely in a downward directions, and we can have a model which we will discuss in the coming classes, that this slope is being pulled by the weight itself, and this pulling force we can apply, we can get it from the component of the weight of this sliding block, or the block which is able to slide, and we can find out what is the force which is acting on this, and we can find that this block has generate some amount of resistance, that will be defined as a strength. So some sliding force will be there and some resisting force will be there on the slope. So similarly, we are trying to find out what is the strength of this joint, which this block is going to take in a actual situation. So we can some amount of such type of joints from the mine. We can take some of the samples from the mine, and we can test in our laboratories to find out what is the resisting strength of such type of joints or similar type of joints. No? So we are taking this block maybe say for example, if I will be fortunate, I can cut maybe I can take a block, maybe this joint is continuing somewhere here. If I can take a same type of rock over here and test in the laboratory, and either not in laboratory, we are trying to test the same thing at this location itself, and we are trying to find out what will be the strength this joint can sustain. And this will depends upon the rock material we have, or the rock material we have, or the type of the roughness we have. So we want to test those things, because we have some sort of a mathematical models are there, that is called the failure models we have already there, which has been developed over the years. But the reality, it is different. We have not have a model which can completely define how the in nature this joint is behaving. We have some successful models are there, but those are just the not we cannot say that it is very accurate for that system. We can just estimate it, no? So to find out, we are going to test this block in the this joint in the into the at the site itself by creating a the setup like this, where we are applying the load on the lower part of the block and fixing the upper block, and there is some amount of we can have some instrument to measure the deformation, whether it can be a dial gauge or whether it can be a LVDT, which will be installed all along the blocks, and it will be measured. And again, we are applying this load maybe in a very slow way. Very if I'm interested for a static loading, we will apply the load in a very small rate of loading we will apply. If I am interested for dynamic loading, we will apply the load in that particular rate. If I am interested for the creep loading, so it all depends upon the type of load which is expected from at that particular locations. Now, so as I told you, when I am going for this test, in situ test or an on-site test, we are applying all types of load. Maybe a creep load we are also applying. We are also applying the cyclic loading into that, and we are trying to find out the properties. No? We are trying to find out the properties of the rock mass. So when I'm going to test for the direct shear test, here my intention is to find the two important properties. One is called the cohesion, and another is called the angle of internal friction. Okay. So these are the two property which is based on a particular model that is called the Moore-Coulomb failure criteria. Based on that, we are trying to find out the two properties C and phi, where we are trying to fit this model, and it will be easy for us to predict the other rock mass as well. Okay. So here we are doing this test, and if you'll see for one of them, the block has been created. You can see this block. This white part is called the block of the rock mass we have, and it is being encapsulated or being reinforced by concrete mixtures. No? It is being reinforced by the concrete mixture all along it. It is a 3D block or maybe cuboid in shape, and from all the sides we are covering it with the shotcrete or the concrete material, so that the other joints, because there are not a single plane of joints are there, but there are numerous of other joints are there. So to find the strength of a particular joint, we are encapsulating it from all the sides, so that other weak planes will not fail. Okay, and then we are applying the load. Okay, then we are applying the load, and you can see in this figure, this is a figure which is representing you that this test is being carried out within below the surface. And you will see that we have the upper roof is there, and then there is a floor, and in the floor we have created a block like this, and the block is being covered by the concrete. And after that, on top of this concrete, we are placing some flat jack of that particular size, and then we have some amount of this some what is called some fillers are there, so that we can fill the gap between the roof and the floor with additional materials, hard iron material, so that the deformation will be less. And then you can find there we are putting some amount of rollers here, so that we can decrease the friction between the two surfaces. We are trying to decrease the friction which is being generated between the slippage of of the surfaces. So we are putting the rollers also, and then we are applying a particular reaction from top of the from these hydraulic jacks. Okay, from these hydraulic jacks once we are fixing, and then we have the flat jacks are there, by which we can apply some constant value of stress is being applied on the block, right? Then when we are working in an underground, there is a one problem, that a space area in which we are going to test it, it is less. So in that case, we have these flat jacks are being installed at some or the hydraulic jacks are being installed at certain angle. Okay, it can depends upon, it can varies from 10 to 15 degrees. So, and it is also important that it will give you some amount of stress which is concentrated below. Hmm. Which will be concentrated below, and it will not try to destabilize the block in other directions. Our target is that all the stress, the effective stress, should work perpendicularly downward, and one stress should perpendicular, it will be along the direction of this joint surface. Now the dotted line is being defined, so that is the joint surface through which we are trying to shear it. Once we are applying the load along this shear direction, it is going to fail along that this dotted line, because apart from that dotted line, all around that, the block is encapsulated, or it is being covered by the material which is stronger than the in situ rock itself. So the only way to fail is that particular rock mass, that direction of the rock mass only. Okay, and once it will fail, we will try to find out what is the failure strength. Okay, and you will see during this process we can develop some sort of a curve like this. Now we are applying this load, and once we are applying the load, we can find out the shear stress. What is the stress is acting on the surface? Say for example, in this figure you will see I am applying a load. In this figure itself you can see this one. If I am applying a load here, Fs, S stands for the shear. If I am applying a load Fs at an angle of alpha, so we can find out what is the shear stress. Shear stress will be Fs cos alpha divided by this area of this sliding surface. Okay, so Fs cos alpha divided by A will be your shear stress. That will be represented by sigma s. Okay, or tau s. That shear we can represent by tau. Okay, So we can call it a tau is equal to Fs cos alpha divided by A. Okay. Similarly, we can find out for what value of Fn, the normal load, this Fs is possible. You will find that as we are increasing this Fn, the requirement of Fs will also increase. As your upper load or the vertical load will be more and more, the Fs will be more and more. No? So we'll find that this Fn will be the normal stress will be Fn divided by A. Okay, so this normal stress will act, or the normal load Fn will act, or the shear force or the shear load is Fs cos alpha. So normal load will be Fn plus Fs sin alpha. Okay, so normal load will be Fn plus Fs. If it is inclined, then one component will be along the perpendicular to this plane also. So the shear load, the inclined shear load will be this one component will be vertical also. So the total normal load will be Fn plus Fs sin alpha divided by A. So the total sigma n is equal to Fn plus Fs sin alpha divided by A. Okay, so you can see that we have this block, and in this block we are applying different number of strain gauges. Okay, we have the 4 strain gauges on top, and 2 strain gauges on the in the direction of the shear stress shearing, and 2 strain gauges in the lateral directions. 2 strain gauges are in the lateral directions, or 2 maybe in this direction, and we are applying the load from this side. Okay, and all along this block we are creating a channel. Okay, so that it can get disconnected from the floor of the rock mass. Okay, so a channel is being created in which we are filling some amount of sand, so that there will be a so it will be disconnected from the rest of the rock mass which is around it. No? And this channel depth is almost 20 mm, or 2 centimeter, and width is 8 centimeter. 80 mm or 8 centimeter or 20 mm or 2 centimeter channel is being created all along this block. Okay, now it can be seen in this figure also. I think it is not shown. So we can create this channel, and with this channel we are applying the load from one of the side. The size of the sample you can see here. In this particular example, we have taken it 700 mm or 0.7 meter to 0.7 into 0.35. The height is 0.35 and the area of cross section is 700 by 700 mm. Okay, now in our lab also this type of machines is there, and in that case we can test up to 300 mm size of the block. And that type of machine is that is highest capacity of the machines available world size. More or less it is most of the machine direct shear machines are of that size only. So if you are going for a larger, maybe 1 meter by 1 meter or 2 meter by 2 meter, the size of this block will increase, and the capacity of this jack which is required for this type of purpose will also increase. Okay, so some of the descriptions are going over written over here, so we can develop one such curve which is talking about the shear stress. We can find it out. Tau will be nothing but it is your Fs cos alpha divided by A, and then we can have the displacement we can measure with the dial gauge, which is in the direction of the shearing direction, and the load will keeps on increasing, and we can find out this inclination of this so you can find out the elastic range, and we can find out the plastic range. So the maximum stress this block will hold or can resist, that is called your peak shear strength, and we are represented by tau peak. Okay, and after that this nature, the after post failure, the nature can be anything, and based on that we can define the other parameters also. Now you can see here we are defining the tau residual, no? Residual strength. And what is the left strength in the material even though the shearing has happened? Okay, so we are defining a term called tau residual. So that is talking about the residual strength of the rock block. Here we are finding the slope. You can see that the shear stiffness we are calling the Ks, that is your this stress versus this displacement, and we are finding out the shear stiffness of this joint. Similarly, there is another parameter we can find out, as we have seen that there are the vertical. We can measure the normal displacement also. So if you can have the normal displacement by shear displacement, we can have another type of plot which is telling you in which direction our block is moving in, because the block is moving. Now you can see here in this figure, if I can assume that the joint are something like this, the block, finally the upper block will move upward in some radial direction. So some x component will be there and some y component will be there. So we are trying to find out the direction in which it is moving, and it will be measured by some angle that is called the dilation angle. And how we are finding out? We are dropping from the peak shear. We are dropping we are finding out the point at which the peak shear stress is happening in this normal displacement and shear displacement curve, and we are trying to find out this angle of inclination of this normal displacement and the shear displacement. So we can find out the angle of the dilation angle. Okay. Similarly, we are also finding another property that is called the Kn, which is being developed with the normal stress, whatever we are applying. It is another type of test where we have to apply this normal stress slowly and slowly, and then we are finding the normal displacement for a particular block. So we can find out the normal stiffness of the joint surface. So here we are finding out the normal displacement. So okay, so this is one thing. So here you will see for a particular value of sigma n, we have this tau peak. Okay, so we are varying this tau peak by increasing this sigma n. And once I'm increasing this sigma n, we can have the different values of uh, uh, stresses. We can tau max we will find. If I'm increasing this sigma n, we have, if I'm increasing this sigma n or Fn, we will find that Fs will also increase. So we can do this test 3 times. We are repeating this test for the 3 times, and we can find it out what is the value of your peak stress. And once we are so that is what we can have. We can plot it. One is called the shear strength or the peak shear strength in y-axis, and x-axis is talking about the normal stress. If you are repeating the test for the 3 times, so we can get a 3 points or the 4 points on this plot. And once we are connecting this one, it will going to give you some a straight line. Okay, for a particular stress range, it will be a straight line, and for a lower value of stress, it may be some curve linear. No? So more or less, we are talking about once it is will be a straight line for a particular value of stress. So we can find it out. The intercept of this is very important, that we are calling it a cohesion. Intercept of this straight line with the y-axis, we are calling it a cohesion. That is an important property. And inclination of this straight line, we are calling it a friction angle, angle of internal friction. Okay, so these are the two. This is the two important properties which is important for you to know, that cohesion and angle of internal friction of a joint. So here we are trying to find out the cohesion and angle of internal friction of the joint. Okay, so cohesion, what is the purpose of cohesion? What do we mean? What is the physical meaning of cohesion? What is the physical meaning of the friction angle? That we have to understand. What is the physical meaning of cohesion? What is the physical meaning of friction angle? That we should know. That how, what is the meaning of this? Means what actually we are measuring if we know the value of C. What does it mean? No? Say for example, if it is not jointed at all. No? So what will be the value of C? And if it is a very smooth in surface, what will be the value of C? What is the value of phi? So if the roughness is being changed, what will happen to the C and phi. So that is also important for us to know. So this is a very important property what we are getting out of this test, C and phi, and that is important for the time being. Rest of the property possibly we will do it for some in your later on, but here it is very important that we can do the one test in a different stages itself, no? In a one test setup, because I told you this test is very costly, time consuming. Okay, so we can test this for different types of normal load at in a one setup itself. By once the failure has happened, then again we are improve, because our important parameter here is your the roughness of the joint. That should be intact, that should not eroded, because once we are doing this sliding, the erosion of this rough surfaces is taking place. So we want to avoid this erosion. Before that is being eroded, we are increasing the stress to another higher level, and we are going to test it till its failure. So in the same test itself, we can have, in the same block itself, we can have a multiple test, and this is going to give us save our time. And with the same block itself, we can have the we can we can find out the properties for the same block itself, and from the same set of roughness itself. That is important. Otherwise, if you go for the another block or the another set of samples, that is going to change the condition also. So we are trying to have a set testing at the same block repeatedly. So we are repeating the test twice, thrice to get the values of C and phi. So minimum 3 tests is required to get the values of C and phi. So tomorrow class we will again discuss. Possibly this is not completed today. So tomorrow again we will discuss it and we will solve some problems on this.